Okay, now we're going. Okay, so today we're going to continue from last week and talk about mirrors, which are very much like lenses, just with one aspect change, and you'll see why. And then thick lenses, which is an extension of the thin lens. Okay, so just to remind everyone, this is where we got to last week, right? Beginning vowels. We have the object leading to a thin lens, which has two spherical surfaces that can have different radii of curvature, and then you get an image formed. And if we know any of the object distance, image distance, or the focal length of the lens, we can compute. If we know any two of the three, we can compute the other, right? And there's also the other form where we can use the refractive indices and the radii to get the focal length, but I just left that out. I actually cited my sources this time. Right, so this is like a visual that I pulled up on lens geometry that there's a question. So this is essentially what I said out loud, but here you can see them. This is what I forgot. Meniscus is what it's called. When you have like a half moon shape. Yeah, so convex means middle is fatter. Concave means the middle is thinner. And you can see that in each of these cases. And for refractive things, basically lenses, convex is associated with positive F, and concave is associated with negative F. That's just a little blurb. And then to just formalize a couple of things here, and also so you have it down for reference, because last week I said them out loud, the sign convention, right? So this one I just said, for SO, which is object distance, SI, which is image distance. So kind of makes sense, right? If your object is before your lens, it's positive. And if your image is after your lens, it's positive. And, the other is just flip. And then for the radius of curvature, for lenses, spherical lenses, and also spherical refractive surfaces, if it curves like a C, then it's positive. If it's flipped, then it's negative. But anyway, that's just, yeah. And in our diagrams, we always assume light goes left to right. That's just that. And then, right, so mirrors, here we are. If you were here last week, you might remember when I talked briefly about how you can actually derive this formula with your just triangles. You can use sine law, you can use cosine law. With mirrors, it's actually very much the same thing. You can see these triangles formed, right? And wait, I won't go through it, but if anyone's curious, we can after. But essentially, you can draw triangles with respect to the phi again, which is which is this one. Yeah. So this one, yeah. And then use sine law, cosine law, and you'll end up with this. But instead of having the refractive indices, because the mirror is just one single reflective surface, right? What you have is just 2/r gives your F. What's your R? It's your curvature once again. But this time, because it's a reflective surface, there's going to be some differences in your sign convention, which I'll get to. But notice how this equation is exactly the same. Actually, in certain textbooks, you'll have it defined with like an extra negative, but as long as you're consistent with everything you're defining, so like as long as Paleo Designer is consistent with itself everywhere, we'll be fine. For lenses, there's only one convention. For mirrors, it's just annoying. There's two conventions, but we'll stick with this one. Okay, I'll get to it. Right. So a concave mirror has a positive focal length instead. Remember how lenses, convex was positive? And then I'll explain in a second. So your object distance is positive when your object is to the left. So like before the mirror. And oh my bad, this should say after. Because after the mirror is like a bounce. I'll correct that in a second. After this, so your image distance is positive when it's still to the left because you're reflecting off of mirror. Yeah, like that is totally the sound light makes. And then your R once again is flipped as well. So think of this as a positive radius of curvature, which corresponds with the F, right? So that's if that helps. Yeah, so the reason all of these are flipped is we want your like object distance, image distance, all those things to be positive, like when your image is formed, like when it's a real image. I haven't talked about that, I guess, but like for a lens, for example, right? Okay, think of it this way. When your image is real, you can actually project it onto a screen. And you want that to be your positive distance, right? So for a lens, it means that image has to come after it, and you can put a screen after it, right? And for a mirror, if your image forms afterwards, then it means your rays are actually diverging out of the mirror, like something like, oh wait, sorry, I'm grabbing my Zoom tools. It's not letting me. 1 second. Oh, there we go. Got it back. I don't say. Okay. So like a virtual image where your image distance is negative, let's say, might look something like this. So you can see how like let's say you're coming in like this. And you can see how the rays are actually diverging. And that's when your image distance is negative, right? So you can't actually form an image on a screen. That's why we want to flip everything around so that, when your image actually comes and forms over here, if I wanted, I could put a screen here and I could see that. So yeah, that's I guess why. Okay, we talked about using the thin lens as a focuser and collimator. With the mirror, I won't go into all of the cases, but here you can see that very similarly, if your incoming rays are parallel, then you end up with an image focused a focal length away from the mirror. So this is the focal point. And this distance is little f. Oh, this distance here is r. Oh, right. And you can see here they did do it to scale, like how f is r over 2. Yeah, and then here is, well, this is a concave mirror and this is a convex mirror, and you can see how there are the angles and everything are the same if your curvature are just opposite, but instead your image will be virtual and you can't project it onto a screen. This is just for us to like conceptualize, really, because the rays, if you back extended them, converge here, but they're diverging instead. And once again, these are parallel, so that means this distance is going to be f. And in this case, this is negative, which makes sense. Your mirror is convex, so f is negative, and also your image distance is behind, is to the right of the mirror, so it's negative. Okay, a couple of assumptions. Once again, paraxial approximation, which means it's like small angle approximation. Sine theta is approximately theta, tan theta is approximately theta. Or like our rays are very close to the axis. So that's a small angle. And then spherical surface. Once again, not perfect, but you can see how close to this region, if we are in the paraxial region, so close to the axis, they pretty much are the same. For one, this gives a paraboloid and a sphere. But yeah, it would be the same for hyperbolic mirrors. Close to here, we can approximate. But what we're neglecting by making these approximations are second order effects, like aberrations, etc., that we'll get to later on. thick lens. Okay, so we talked about the thin lens, but what we're assuming here is that the thickness is negligible. So effectively, so D is approximately 0, or we can treat it as such. So what we're really doing is treating this surface and this surface as like overlapping. So there's no thickness whatsoever. And over here, this is a more realistic model because typically your lenses, like the glasses I'm wearing on my face right now, have some thickness. And relative to, like the curvature. Yeah, relative to like all of the other distances you're working with in here. So you actually find that there's a very nice way of treating this. If you've looked at Stephanie's section in the SCD, she actually derived it using some ray transfer matrices, which are convenient. But I'll go over like just, a super abbreviated version today. So essentially what you have are principal planes. Principal planes in an optical system lets you basically treat your rays coming into it and your rays coming out of it as it's a reference point for a simplified system than what you actually have. Okay, let me actually explain. So essentially what you have here is let's say your image is at a focal distance away from your principal plane. Then what you have is that the rays coming out of it are going to be parallel, coming out of the entire lens are parallel. Notice how this is like very reminiscent of what we had with a thin lens when there was no distance at all. Here we do have distances, but where this focal length, effective focal length, that is, like takes effect, is somewhere inside the lens. So we have two focal planes. If I were to go through derivations, you would be able to see why, because we have one refractive surface, and then we have like this region inside with like a different refractive index than the outside, right? Because this is a higher refractive index, and then you have your second surface. But essentially that's what defines a principal plane. So here's the first one, and here is the second one. So we call them primary and secondary, or we can also call them we can also call them front and back focal planes. No, principal planes. My bad. That was a okay.
Sorry, the plane is the bolded line, right? It's not the curve.
This one. Yeah.
So what's the dashed line then?
The dashed line would be. Let me actually check this textbook and get back to you.
Okay.
Yeah, I know the page I got it off of. Okay. Yeah, good question. Let me see. It looks to me like. Ooh. Okay, no, I'll definitely just check and get back to you. Okay. So how do we compute where these focal planes are? Because those are the places that we can do our math with respect to, right? So it turns out, if you know the focal length, if you know the refractive index of the lens, if you know the thickness of the lens, and your radius of curvature of the second surface are 2, if you know these 4 things, you can compute this one. And it's not too hard to imagine that, to compute the second one, you would just need, instead of R2 here, you would just need R1. So what does this actually let us do? Oh yeah, and you can see that H1 and H2 are with respect to the vertex of the lens, vertex being the outermost point. So here's H1 and here's H2, right? So essentially what we get is that for the thick lens, these planes also happen to be the nodal planes, which means that whatever a ray enters, let's trace the second ray. You can see how it enters here, but then it just kind of jumps over here and then continues on its merry way. That's very nice, because once we know where these planes are, we can just ignore the thickness of the lens, really. So yeah, nodal planes are essentially where your ray enters it and exits it at the same angle. And here you can see it's the same height and the same angle. So it's very, very nice because all we have to work with is just the thin lens equation for the Gaussian formula or Gaussian equation. And the only condition is we compute the location of our principal planes. Yeah, this is a very nice textbook, by the way, Optics by Eugene Hecht. I don't know if Jason mentioned it back in his days. I found myself downloading it twice, like a year apart. Whoops. But yeah, it's pretty nice. It's very comprehensive and it's available in multiple, not necessarily legitimate ways. I said this on recording. It's okay. It's okay. Okay, so that is it. That is it. Okay, yeah, questions? Oh, is analysis of an optical system's virtual image is useful in cases if they have no physical meaning? Oh yeah, no, it very much is, because when your rays are actually, diverging, that's what virtual images are, right? Like here we have a lens. Oh no, okay, there we go. One sec, let me annotate. Okay, here, if we were to put our image here, let's say it's a flower, within the focal length, what would actually happen is, you would have light going like this, and then instead of converging, it would actually go out and diverge, like it would go like this. So where is it diverging? And like, how do we quantify this divergence, right? Then we would actually use, we just back extend these. That was not very well back extended, but this is a virtual image of a flower. So absolutely. And what else do we know? When you put lenses in series with each other, so let's say we had another one here, thin or thick, not a big deal. You can actually make this, which is a virtual image, enter this system. And then given that, it's outside the focal length of this lens, it'll actually form a real image out here. So very much, we do care about virtual images. This is very poorly drawn. Let me know if that makes sense. Because whether or not this forms an image or not is dependent on where this is with reference to this lens, not whether this is real or virtual. As soon as this with respect to this lens is placed in a location that qualifies it to form an image, which is in this case outside of this focal length. Let's say this was F for this lens, this is out here, then we can form an image. Yeah, hope that answers.
Cool. Yeah, thank you.
Yeah. Okay. Anyone else got any questions? If not, I'm gonna end the recording here, but feel free to drop any question in the chat still. Oh, whoops. Stop recording.